Alright, so another request for exercise 8.3, and so this is the case of our parallel and series reactions in an isothermal CSTR. Okay. And again, I'm going to point out my typo. Selectivity of B over C, my desired over undesired product, so moles of B over moles of C, or concentration of B, this should be concentration of C, right? NB, CB, NC, that should be CC. Okay. Alright, so let's take a look at the code. Alright, okay, so we have a function with no inputs, that's fine. Okay, so it looks like we're trying to list our stoichiometric coefficients. They're all underlined. They're all underlined, which means they're not used at all. Okay, so we'll need to take note of that. But just, there's nothing in the documentation. Looking at your stoichiometric coefficients, this would be a case of your series reactions, right? I'm going to have A goes to B, and then B goes to C, right, in reaction 2. So reaction 1's A goes to B, reaction 2's B goes to C. So that's fine for series. Rate constants. This would be the case that both rates constants are the same. Okay, and this is what you're going to vary. You're going to look at K02 as a multiple of K01. So you look at K02 is 0.1 times K01. K02 is equal to K01 like you have here. And then K02 is going to be 10 times K01. Okay, so let me just write K01 here. Just so eventually you can add a multiple there and get it. So yes, activation energies are the same. Converting to joules so that you can use R's and joules per mole Kelvin. And you get temperature, okay? That's great, okay? And then you go and you calculate your rate constants, okay? That's fine, okay? But I'm just going to go ahead and even put those right up here. Since it's an isothermal CSTR, right, I can just go ahead and pre-compute this, right? Temperature is constant, okay? All right, so now I look at your for loop. Actually, let me make this bigger so you can see everything, okay? So again, stoichiometric coefficients, we're going to take a look at because they're not used. I changed K02 to K01, and then I just copied and pasted K1 and K2 up here. Alright, so if I look at your for loop, okay, no need for a semicolon there. And we should be indenting altogether, but I'm going to indent that just to make sure it's clear that it's in the for loop. Okay. So first thing is, so you create this anonymous function. So we create an anonymous function because fsolve expects a function with a single input and a single output. All right, fsolve is going to expect in-air function with a single input and a single output. So you're creating an anonymous function that's going to have a single input C, where C will presumably be our vector of concentrations A, B, and C that we're trying to solve for each value of tau. Okay, and then we're calling CSTR mole balance, which presumably is my general air function. And you're passing to it C. That'll have inputs of C, TK, K1, and K2. Okay, where T, K1, and K2 would have been defined up here. All right, so the first thing that already jumps out to me that a few of your classmates have been making is T. Well, actually, T is okay here because T is a scalar. Okay. Alright, it's just my loop index. So in your case, that's okay. Okay. We'll come back to that in a second though. So C, TK, K1, K2. So input C, T, K1, K2. That's fine. Okay, and then one thing I see is you redefine your stoichiometric coefficients here. Okay, so that's fine. Okay. The other thing is you also define them up here. So what you could just as well do is you could make them inputs to your anonymous or to your air function as well. That way you only need to define them in one place. I often like to put them up top, like here, so that when it comes to, say, a parallel reaction, all you need to do is update those stoichiometric coefficients up top. Okay, so let me just go ahead and I'm going to delete these down here. And I'm just going to add these to my inputs. Okay, this is optional. Let's just define our stoichiometric coefficients in one spot. All right, so now looking at your error function, you unpack C. That's great. Again, unpacking is not necessary. I like to do it though, so I can write my rate expressions in a form that makes sense to me. All right. So this is fine, right? So K1CA is R1, okay? And again, this is preference. When you look at my solutions, I like to define, say R1 as K1CA, then just type R1 in here, just so it helps me keep track of things. But that looks okay. Okay, so that would be the right-hand side of your mole balance design equation. So then over here should be in minus out. So essentially what you've done is you just plugged in your initial conditions already, right? Ca naught is just 2 molar, that's fine. Cb and Cc naught are 0, and so that's also fine. Okay. Just for completeness, okay, I'm going to define a Ca naught is 2, and again, you can add comments that are more detailed than this, and you should. Okay, but when we have parameters like this, I like to define them up here. That way, if I ever encounter another series or parallel problem, right, I already have code then that's going to need minimal modification to solve for that case. So I'm going to add Ca naught, Cb naught, and Cc naught. And actually, I should have stuck with your notation of big A then. Okay, so let me make big A. Ooh, big B, big C, big A, big B, and big C. Okay, so that looks fine. So then I can update this. Ca naught, Cb naught, Cc naught. And then I can list my, well, I don't even need to list them. So then my mole balance design equation can just be Ca naught minus Ca. Cb naught minus Cb. Oops, Cc naught minus Cc. Cool. And this is series. Yep, so that R2 is correct. Now, even if you were to define, R1 and R2, here separate variables, it would have to come within your error function because Ca and Cb are going to be functions of tau. Okay, so that looks fine. Now, if I look at this, your code still won't work. Okay, so now one issue I see is when I look at your fsolve call, so you point to your anonymous function, which has a single input, okay, and it is going to have a single output, all right? Fsolve expects a function with a single output. But when I look at my output, all right, my output's going to be a vector of length 3. Right? Fsolve is going to keep iterating, in theory, on concentrations A, B, and C until it returns a vector of 0, right? Until each one of these expressions is 0. And so what I need to give it then as an initial, here is going to be initial guess, right? Remember, you could even use fsolve with an initial guess. Okay, but that initial guess has to be a vector of length 3. So we can make it 1, 1, 1, but it's going to have to be a vector of length 3. This tells fsolve that it should expect an error function with 3 variables, so you're solving for 3 variables. Okay, and this should, in theory, work. Okay, now this isn't complete and correct, but this should work. So let me minimize this, and let's run it. Okay, so this is just called homework 8_3. Okay, and so I'm just looking to see if we get any error messages, and we do. Array indices must be positive integers or logical variables. see what we have. So first I'm going to go look at line 42. Okay, CA naught's just a scalar. CA is a vector as you unpack it. Plus T. T is going to be a scalar because it should just be your loop index variable. Stoichiometric coefficients, those are all scalars that I'm passing. Let's look at K1 and K2. Those are definitely scalars. It should be an issue. Those should definitely be scalars. Oh, T times. Okay, I forgot the multiplication sign. So when it's T, then parentheses, it's assuming it's going to calculate this, and that's going to be an integer index to some vector T, or T has to be some function. Got it. All right, so you didn't have the multiplication sign here, so it's first interpreting T as being some undefined vector. All right, well, in fact, T is a scalar. All right, so actually, yeah, so T would be a known variable in this function workspace. And so parentheses following it then would be pointing to a particular element of T, and it's telling you that, you know, when it does this calculation, it's an invalid an integer index. All right, so let's try running again. And again, we're just looking to see if we have any errors. It doesn't look like we have any. It's probably going to take a while to run. Okay, well, not too long. Right, you look at 1,000 different temperatures, and it's going to return back that last iteration. Bam, right? Good, so it works. All right, so, you know, if this were my code, what I might do next, okay, is, you know, this is great. This is just going to return CA, CB, and CC for the last iteration, right? When I say it's going to return it, because res, right, is what's getting returned. And that's okay, but then, you know, then there's no need for a for loop. I could just do the calculation at T, or tau of 1,000. Okay, what might be more useful is collecting your variables as vectors. And so the easiest way to accomplish this, okay, is if I stick with T. Now I could do T as 1:1,000, okay, but I'm going to do linspace, and I'm going to start at 0. I'm going to go from 0 to 1,000. So linspace is just nice because it's going to create a vector of 100 equally spaced points between 0 and 1,000. If you wanted to add a third argument, you could set how many points it can be. All right, and so if I wanted 1,000, there's 100, there's 1,000. And so this is just nice because using colon operator, sometimes the number of data points you have can get a little out of control. Okay, and so then what I'm going to do is I'm going to create collection vectors to collect the concentration of A, B, and C, which I'm solving for each value of T. So I'm going to do CA, and I'm going to initialize this vector as zeros, and I'll just do size T. So it's going to be a vector of zeros, the same size as T. CB will be zeros, size T. CC will be zeros, size T. Okay, and then I'll update the for loop. So loop for I, and now I'm going to do 1:length T. All right, first element integer index is going to be 1, then length T will tell you how many elements are in T, so you'll loop over all of T. And so then here now, where I just need to update is, I don't want to pass T, because now T is a vector, so I want the ith element of T, right? The value of tau for that given loop iteration. Okay, cool. And then to make it complete, okay, so res is going to be a vector of length 3. Okay, and now this is where unpacking is useful in my mole balance. Right, I define the first element of C to be A, second's B, third C. So res is going to be ordered as CA, CB, and CC. Okay, so if I want to collect these now, all right, the ith value of CA, all right, the value of CA for the ith tau value, okay, would just be equal to res 1. CBI be res 2. CCI would be res 3. Okay. And so, all right, just to, for completeness, to show you what this, looks like. Well, how do we want to return this? Let's, instead of returning res, let's return all these back. So I could return T, CA, CB, and CC. Okay, I want to copy and paste for when I call it. All right, so now if I call it, okay, and then express the output, right? So now I have CA. Actually, I could even just double click it. It opens up in like a Excel sheet. So now I have a vector of my CA values, right? Initial concentration is 2. So at 1,000, it's 0.7372, right? I've got a vector for concentration of B, which starts at 0 and increases. My vector of C that also starts at 0 and then increases. And then I have a vector of my taus. So I could match those up to my concentration vectors and see exactly what I have. All right, and so that's great, outputting all that. All right, but I could also plot it. Okay. So, you would definitely need to make it fancier, but I could plot T versus CA. I could plot T versus CB. I could plot T comma CC. Why is this underlined in red? Right? And so then if I run it, I could just plot my results. Right? And you could label it, you could look at longer times. Life is good. And I made a comment about lint space. Lint space is nice because I could readily, if I want to look at longer times, see when things start to plateau, I could readily make my upper bound say larger, say give it another 0. So do 10,000 seconds. And it's still only going to be 100 data points. All right, and so it should still run pretty quickly. And then if I need finer resolution, I can readily add that third argument and make it look at more data points. Okay, but this looks good, and this is characteristic of my series reaction, in which my concentration of B is going to go through an extremum. Okay, cool. Okay, so there's still plenty of details that you need to add to your code to get it working for the problem, but that should get you started. One other thing I might think about is, what we're looking at are different scenarios of, K02 is multiple of K01. So I would think about making that an input. All right, so that I can just define K02 as a multiple of K01. All right, and so if I wanted to look at that case where they're the same, right, I get the plot we just saw. But if I want to make K02 a tenth of the value of K01, I can just make K01 an input, run it, get that result. Maybe I want to make the time longer. If I want to look at K02 as 10 times K01, right, I can just update the input and I have it. Okay, so there's still work to do in terms of making this look nice, calculating selectivity and things like that. But hopefully, that gets you to a good place in terms of being able to get set up and running. Let's see, major issues, if I recall them, is in your original fsolve call, you only had a single initial guess here. Okay, so remember when I'm solving for 3 unknowns, like I am in this case, then I need an initial guess for each of those variables I'm solving for. But I think that was it. And then once you fix that, the error was you had forgotten that multiplication sign there. Okay, but otherwise, working with fsolve, you had the right idea in terms of the mole balance, or the error function, which is our mole balance, that you need a function with a single input and single output, which is then just remembering you need an initial guess for each of the variables you're solving for. Okay, and one of the annoyances with fsolve is this is an initial guess. So if you ever find it not working, you might just play with your initial guess, right? Of course, the better you make your initial guess, the better it is. But in the chapter we use rand a lot, just because for some problems I've encountered, making them all the same doesn't quite work. Okay, but hopefully that is enough to get you going.